Differential Equations and Introduction, Lesson 1. So we're going to start off by talking about what a differential equation actually is. And it's an equation that involves at least one derivative. So here's an example. dy by dx equals 4x, a very simple differential equation. Now we would call this a first order differential equation, and that's because it only involves a first derivative. Later on, in further maths, you'll go on to study second order differential equations, which involve the second derivative, so equations that contain d2y by dx squared. Now, let's think about what this equation actually tells us. It tells us that dy by dx, i.e. the gradient, is 4x. So if we think about the original function y, which has been differentiated, this has resulted in dy by dx, which in this case is equal to 4x. Now, if we're going to try and solve this differential equation, we want to know what is y. Well, how do we get back to y? Well, of course, we integrate. Now, this is a very simple differential equation, so we can simply integrate. So y would equal the integral of 4x with respect to x. And again, this is a very simple integral to perform. So y equals 2x squared plus a constant. Now, what we have here is a solution to our differential equation, because of course it doesn't matter what c is. When you differentiate this, because c is a constant, we will always get back to dy by dx equals 4x. So we call this a general solution. Now, what does it represent? Y equals 2x squared plus c. Well, we can sketch this because, of course, this is the equation of a graph. Now, what the graph will look like will depend on the value of c. If c is equal to 0, then of course we have a parabola that passes through the origin. If c is equal to, let's say, -2, we'll have a parabola that looks like that. If c is equal to, let's say, 3, we'll have a parabola that looks like that. So here we have y equals 2x squared minus 2. Here we have y equals 2x squared. And here we have y equals 2x squared plus 3. It's almost like a collection of curves which are sort of parallel to each other. Now, we would call this a family of solution curves. And of course, infinitely many of these exist because c could, in theory, take infinitely many values. Now, sometimes we're given a little bit more information. We're given something which we might refer to as boundary conditions. Now, boundary conditions will give us some information about the curve. So, for instance, we might be told that the curve we're really interested in has an x-coordinate of 2 when y is equal to 3. And what we can do is substitute these into our general solution, which gives us 3 equals 2 multiplied by 2 squared plus c, and from there we can calculate that c is equal to -5. This then allows us to be more specific about our solution, and we can say that y equals 2x squared minus 5. And this is called a particular solution. the boundary conditions have allowed us to identify which of the solution curves is the actual answer to our question, but again, only for this specific set of boundary conditions. Now, we're shortly going to have a look at how we can form differential equations, but to do that, we're just going to briefly recap the concept of rates of change. It's really important that we understand rates of change, both increases and decreases, if we're going to be able to successfully set up differential equations for different situations. So let's have a look at some very simple examples. The rate of change of temperature. Now really, when we're talking about rate of change, we're talking about how fast something is changing with respect to time. If it's with respect to another variable, then that other variable would have to be mentioned. So the rate of change of temperature with respect to time, dt by dt. And of course, capital T represents temperature, and in this case, lowercase t represents time. So that derivative represents how fast the temperature is changing over a period of time. The rate of change of the volume of an object. Again, if V represents volume, this is dV by dt. What about the rate of change of velocity? Well, I'll use a lowercase v for velocity here as opposed to an uppercase V for volume here, and that is dV by dt, which of course you know is equal to acceleration. The rate of change of velocity is the acceleration. And the rate of change of displacement, I'll call displacement lowercase x, that is dx by dt, which again you know from mechanics is equal to velocity. Now, being able to convert the wording relating rates of change of different variables into the format of a derivative will be really important later on when you proceed to solve more complex problems involving differential equations. So we're going to start off by having a look at how we form differential equations. At this stage, we're not going to actually solve any. That will be in the next lesson. We're simply going to look at how we form differential equations. So, example 1, the number of bacteria increases at a rate that is directly proportional to the number of bacteria present. So, the number of bacteria increases. This tells us we're talking about a derivative. Rate tells us we're looking at time, so we're talking about dN by dt. Now it's directly proportional to the number of bacteria present, which means it's directly proportional to n. And we have a proportionality statement. Now, if we want to form our differential equation, we then need to replace it with dN by dt equals kn. And this is some form of constant of proportionality, some sort of rate constant. You might be given information in a question which allows you to work out what k is. Let's have a look at another example. The volume V of a balloon is decreasing at a rate of 3 centimetres cubed per second. Now the units here can be very, very useful because they will give you a bit of a hint about what the derivative actually is. And you can see here, this is the unit of volume per time. So it tells you it's dV by dt. So dV by dt is equal to negative 3. Now, why is it negative? Well, it's a decrease. So the rate of change of the volume is decreasing at a rate of 3 centimetres cubed every second. So every second, the volume is reducing by 3 centimetres cubed. Now, the fact that it's equal to a numerical value and it's not actually dependent on anything else tells us this is a constant rate of decrease. So every second, we're losing the same amount of volume. Example 3. The acceleration of a particular object is directly proportional to the square of its velocity. That's a useful statement there. Let's start here. So, the acceleration is directly proportional to v squared. A is equal to k times v squared, where k is some kind of constant. Now, previously we talked about what acceleration means. Acceleration is the rate of change of velocity, dv by dt. So dv by dt equals kv squared. There's a starting point. But we're given another piece of information. When the object has a velocity of 12 metres per second, it is decelerating at a rate of 2 metres per second squared. Now, this tells us that dv by dt, the acceleration, must be -2. Why is it -2? It's -2 because it's a deceleration. So -2 is equal to k multiplied by the velocity squared, so 12 squared. So this gives us k is equal to -2 over 144, or -1 over 72. This then allows us to form the differential equation. Putting this information together, we can say that dv by dt is equal to -1 over 72 multiplied by v squared, or v squared, or -v squared over 72.